So so here we have an angle bracket which is made up of a sheet material of some thickness, uniform thickness. So aluminum plate which is with a mass of 13.45 kg per square meter. So calculate the principal moments of inertia about the origin O. So we have to calculate the moments of inertia about this O, about this X, Y and Z, and also you have to find out the directions cosines of the principal axis of inertia. The thickness of the plate is small compared to the other dimensions. So this has to be divided in three parts. So one this rectangular plate, one this rectangular plate, and one this circular plate, and the moment of inertia of this rectangular plate and this rectangular plate have to be added, and this has to be subtracted. So this we call 1, this circular portion of the plate we call 2, and this we call 3. So now actually for this rectangular plate we know the moment of inertia about X axis and Z axis, and the moment of inertia about Y axis will be sum of these two. And you know for thin uniform plates the mass moment of inertia is closely related to area moment of inertia. So here for this Ixx, so Ixx1, that means for 1 this Ixx is 1/3 m1 b square. So m1 about x, that means b is this one, so 1/3 m1 b square. So and about this Izz, it is 1/3 m1 into a square, where m1 is this mass per unit area into area. This is mass per unit area and this is area. So this is the value of Ixx. So please check the calculations. So and the moment of inertia about this Y axis is the sum of 2, and this is this much. So and for the product of inertia, see, this Y axis is actually the XZ plane. The Y axis starts from the XZ plane. So Y plane means the XZ plane. So the products of inertia which is having Y in it, is 0. So for this 1, that is 1 means for this rectangular plate, Iyz will be 0, Ixy will be 0. But Izx will not be 0, and for Izx you have to, from the centroidal or from the center of mass, you have to add this amount from parallel shift of inertia. So Z1x1 is symmetric axis. So about this Iz1x1 is 0, but you have to shift, and the shift you have to measure from here to this XZ system, to the center of mass XZ system. So Rx1 is the shift of X and Rz1 is the shift of Z. So you have to multiply 0.210 by 2 and 0.1 by 2. So this is Izx1. So now for this 2, the mass is mass per unit area into area. So this is the mass. Ix2x2 you know is Ix2x2, x is here. Ix2x2 is 1/4. Ixx of 2 is Ix2x2, which is 1/4 m2 r square, plus you have to shift it to here. So x. So this square from here to the center of mass rz2 square you have to add, and this is the moment of inertia. And Iy2y2 is summation of these two. Iy2y2 is about this. So Iy2y2 is about this y2. This is the moment of inertia. Then the distance between, perpendicular distance between this y2 and this y, which is this square plus this square. So this is, and this is the value you get. And Izz of 2, Izz of 2 is about this. So about this you know, and then you have to shift by this amount. So about this is 1/4 m r square, that is about a diameter, 1/4 m2 r square, and we have to shift this amount. So this is the moment of inertia. And here again y is a plane of symmetry. So any product of inertia having y in it will be 0. But Ixz2 will be Ix2z2. That means Ix2z2, since x2 and both x2 and z2 are axis of symmetry, Ix2z2 will be 0. But you have to take the shifts. So the shifts have to be measured from here and here, and accordingly, if it is in this direction in x, it has to be positive, and if it is in this direction of z, it has to be positive. So here both are positive, and you put this value and you get this. And then for this square plate, this is the mass Ix3x3, that means Ixx of 3. You can get this about Ix3x3, which is 1/12, and then you can add this amount, add this, take into account the effect of this shift, and you get 1/3 mass into this length square. So you get this, and Iyy is, so 1/3 mass into this length, so this length square, so this, and Izz is so summation of these two, so this. Since now here z is a plane of symmetry, anything having z in it will be 0. So and Ixy will be Ix3y3, that is the centroidal axis or the center of mass axis. Ixy will be Ix3y3, which is 0 because of symmetry, plus m3, and shift in x and shift in y. The shift in x has to be measured from here. The shift in x has to be measured from here, which is this, and it is in the negative y direction. So the shift in x is 0.120 by 2 with a negative sign in it, this one, and the shift in y and the shift in y is it has to be measured from this y, so in this direction. So it is 110 by 2. So this is 110.2 and this is the value. Now once you do this, so segment 1, 2, 3, so 1 and 3 they have to be added and 2 have to be subtracted, and this is the net result. So this is Ixx, this is Iyy, this is Izz, this is Ixy, this is Iyz, and this is Izx. Now you can put it in a matrix: Ixx minus Ixy minus Ixz. This is minus Iyx, Iyy minus Iyz, and this is minus Izx. This is minus Izx, minus Izy, and minus Izy, and this is Izz. So for getting the principal moments of inertia, you have to solve this eigenvalue problem, and the eigenvalues will give you the principal values and the eigenvectors will give you the directions. So we have done it in Octave, and you know Octave is very similar to MATLAB. So this xi actually is the moment of inertia matrix, and this is the eigenvalue command, and in V there will be the eigenvectors in column, and in D the diagonals of D will give you the eigenvalues. So these three are the principal values of moments of inertia, and for this is the direction. So you may wonder what direction is this. This direction is, suppose you take your x, y, z like this. Suppose you take your x, y, and z like this. Then this direction means go 0.933 along x, go minus 0.17 along this, and go this. So this is this direction. So this direction is actually, you can get by this. So about this axis, if you calculate the moment of inertia, then you will get this value. So this is actually the meaning of this. Similarly, about in this direction you get this, and in this direction you get this. So alternative is, so you write this like this, write the eigenvalue problem like this, and you multiply it with an identity matrix. So you can multiply it with identity matrix, because just writing LMN and just try pre-multiplying it with the identity matrix is same. Now you subtract and you get this, and this will have non-trivial solution only if the determinant is 0, and once you make the determinant 0, that gives you a cubic equation in lambda, and this is the cubic equation in lambda, and if you solve this, it will give you 3 roots, which is same as what you are getting from here. So I request you to repeat this in any software you like. So let me stop here.